All right, let's get started. Today we're looking into something really fundamental, toxicology. And, it might sound a bit dry, maybe like a science lecture, but honestly, getting a handle on how different substances, chemical, even physical things like certain dusts can affect us, well, it's key for safety. We've got some great notes here, and the aim is to pull out the insights that really matter day to day.
Exactly. We're going to explore those core ideas. How do these things get into your body? What defenses does your body actually have? Which, spoiler alert, are pretty amazing.
Okay.
What harm can they cause? And crucially, how does the science help us figure out and hopefully prevent that harm? It's like getting equipped with essential safety knowledge.
Okay, so let's kick things off right there, the basics. What exactly is toxicology? Can you break that down?
Yeah, simply put, it's the study of the harmful effects of toxicants on living things. And when we say harmful effects, it's, anything bad, from minor irritation right up to really serious illness.
Right.
And toxicology looks at both the type of harm, like is it your lungs, your skin, and also the amount of harm related to how much you're exposed to. It's the what and the how much.
And a toxicant. That sounds pretty intense. What qualifies?
It's really just any agent that can cause harm. So chemical agents, sure, dusts, fibers, solvents, things like that you might find at work, but also physical agents. The notes mention asbestos, which is a perfect example. It's a physical fiber, right? Not a chemical reaction causing the problem, but the physical presence of those tiny fibers lodging in your lungs.
Wow, yeah. Asbestos is a big one.
Or think about excessive noise or certain types of radiation. They're physical agents too, causing harm. They all fall under that toxicant umbrella.
Okay, that makes sense. So these potentially harmful things exist, but what turns a substance into an actual threat? There's a difference, isn't there?
Yes, and it's a really critical difference. It's toxicity versus toxic hazard. Toxicity is like the built-in ability of something to cause harm. It's just a property of the substance itself. Toxic hazard, though, that's the likelihood that harm will actually happen based on how you're exposed. Think about it. A super toxic chemical locks safely away. Low hazard.
Right, unless something goes wrong.
Exactly. The hazard depends on the transport, the usage, the potential for you to actually encounter it. It depends on the exposure conditions.
Got it. Like a poisonous frog behind glass versus one hopping on your desk.
Precisely. So let's talk about those encounters. How do these toxicants actually get into the body?
Yeah, what are the pathways?
Well, the notes lay out 4 main routes. First, maybe the most obvious, is ingestion. Swallowing something. It goes into your stomach, your digestive system.
Which is why you have rules like no eating or drinking in labs or workshops, right?
Exactly. Crucial safety rule. Second is inhalation. Breathing stuff in gases, vapors, tiny particles through your nose or mouth down into your lungs.
And that's a big one, I gather.
It's a huge one because your lungs have this enormous surface area for absorption. The notes say around 70 square meters.
70 square meters, that's wow.
Yeah, think of all those little air sacs, the alveoli, maybe 300 million of them. It's a massive area for things to cross into your bloodstream. And particle size really matters here too.
How so?
Well, larger particles, say bigger than 5 micrometers, they usually get filtered out in your nose and throat. But smaller ones go deeper, like 2 to 5 micrometers might reach the bronchioles, the smaller airways.
Okay.
And anything under 1 micrometer, that can get right down into the alveoli, the deepest part. So what you inhale and how big it is makes a big difference in where it ends up.
Suddenly makes you think a lot more about air quality. Okay, what are the other ways in?
Third route is injection. This is where a toxicant gets in through breaks in the skin cuts, puncture wounds.
Like sharps injuries.
Exactly. Needle stick injuries in healthcare or mishandling sharp tools. The notes specifically mention improper needle storage as a potential issue. Proper handling and disposal are vital.
Makes sense. And the last one?
Dermal absorption. That's when something passes right through your skin into your bloodstream. That's why protective clothing, gloves, aprons is so important when handling certain chemicals.
Even though skin is a barrier.
It is. That outer layer, the stratum corneum, gives some resistance, but many substances can still penetrate, especially with prolonged contact.
So the route it takes really changes the risk profile. I think the notes had a chart showing that, figure 2.1.
Yes, exactly. It shows how the concentration in your blood changes over time depending on the route. Injection usually gives the highest, fastest peak.
Right into the bloodstream.
Yep. Then usually inhalation is next fastest, maybe not quite as high a peak. Then ingestion is slower, lower concentration. And dermal absorption is typically the slowest and results in the lowest peak concentration.
And that has direct safety implications, right? How quickly you need protection.
Absolutely. If the risk is injection, your controls need to be immediate and foolproof. For dermal, you might have a bit more time, but prevention is still key.
Okay, so these things get in, but our bodies aren't just sitting ducks, are they? What do we do to fight back?
Definitely not sitting ducks. Our bodies have some pretty sophisticated defense mechanisms. The notes highlight 3 main strategies. First is excretion, just getting the stuff out.
Like waste removal.
Pretty much. Kidneys are major players, filtering blood and getting rid of waste, including toxicants in urine. The liver helps too, putting some substances into bile, which then leaves in feces.
Okay.
And even your lungs can excrete some things, volatile stuff like maybe chloroform or alcohol. You breathe it out.
Interesting.
And there's a slight difference depending on how it got in. For things you ingest, inhale, or absorb through skin, the liver often gets a first pass at processing it before it can be excreted in bile. Injected stuff might bypass that initial liver step.
And size matters too.
Yeah, molecular weight plays a role. Generally, bigger molecules, maybe over 300 molecular weight, often go the bile route. Smaller ones tend to be handled by the kidneys via urine.
Okay, that's excretion. What's the second line of defense?
That's detoxification, or the technical term is biotransformation. This happens mostly in the liver.
The liver again. It's busy.
It really is. It has enzymes that chemically change the toxicant. Usually the goal is to make it less harmful and, importantly, more water-soluble.
Why water-soluble?
Because that makes it much easier for the kidneys to grab it and excrete it in urine. So the liver basically disarms it and tags it for removal.
Clever. And the third way the body deals with these?
The third is storage. Sometimes the body can't immediately get rid of something, especially if it's fat-soluble. So it gets stored away, often in fatty tissues.
Yeah, good or bad?
It's complicated. It gets it out of immediate circulation, which might seem good, but it can lead to long-term issues or delayed effects. And if you later lose weight rapidly, those stored fats break down.
And release the toxicants back into your system.
Exactly. You can get a sort of secondary exposure from your own fat reserves.
Wow. Okay, so the body tries its best, but sometimes these defenses are overwhelmed or the toxicant causes harm anyway. What kind of harm are we talking about?
Well, the notes have a table, Table 2.2, outlining a whole range of potential adverse effects. It's quite sobering, really.
Like what?
Things like cancer, that's carcinogenesis, damage to chromosomes, your genetic material, that's mutagenesis, causing birth defects, teratogenesis.
Really serious long-term stuff.
Absolutely. And then many toxicants target specific organs. Hepatotoxicants damage the liver, nephrotoxicants the kidneys, neurotoxicants the nervous system.
Okay, I see the pattern.
Dermatotoxicants affect the skin, hemotoxicants the blood, pulmonotoxicants the lungs. It's, quite a list.
Definitely underlines why prevention is so critical. Are there also maybe less severe effects that can be measured, perhaps as warning signs?
Yes, definitely. And these are really important for things like occupational health monitoring. The notes mention changes in breathing capacity.
How do you measure that?
Often with spirometry. It's a breathing test. It measures things like your vital capacity, how much air you can breathe out fully, or FVC, forced vital capacity, and FEV, the amount you can force out in the first second. Reductions can indicate lung irritation or damage.
Okay.
You can also sometimes see nervous system effects with tests like an EEG, an electroencephalogram. Blood tests can show changes in blood cell counts or enzyme levels. And of course, just examining the skin can reveal dermatotoxic effects. These are all potential indicators of exposure.
This is incredibly complex. How do scientists even start to figure this stuff out, to know what's dangerous and at what level?
Yeah.
That must involve specific studies.
It does. Toxicological studies are designed precisely for that, to measure and quantify the effects of suspected toxicants. There's a process.
What are the steps?
Well, first, you have to clearly identify the toxicant itself. What is it? Its properties. Then figure out the target. What part of the body does it affect? Then you observe and measure the response, what actually happens.
Right.
And crucially, you need to test a range of doses. How much causes what effect? And finally, decide the test duration. Is it a quick one-off exposure study, acute, or a long-term repeated exposure study, chronic?
And picking the right test subject, the organism. must be vital if you want the results to mean something for humans.
Absolutely critical. You need an organism where the biological processes are similar enough to ours to make reasonable predictions. It's not always perfect, which is why researchers might use various animal models, cell cultures, maybe even computer simulations now.
And underlying all this is that famous saying,
"The dose makes the poison," attributed to Paracelsus centuries ago, but still absolutely fundamental. The amount you're exposed to is the most critical factor determining if there's harm and how much.
even water can be toxic in huge amounts, right?
Exactly. It's all about the dose.
Which brings us neatly to the dose-response relationship, how the amount relates to the effect.
Yes. This is a cornerstone of toxicology. It describes how the chance of harm and the severity of that harm relates to the dose. But it's not simple, because individuals react differently. Figure 2.2 in the notes shows that classic bell curve. Same dose, different responses. Why? Age, sex, weight, health, genetics, lots of factors. Some people are more sensitive, some more resistant. Most fall in the middle.
So not one size fits all. How do scientists graph this relationship, this variability?
They use dose-response curves. Figures 2.6, 2.7 show examples. You plot the dose, usually on a log scale, against the percentage of the group showing a specific effect. It often gives you an S-shaped curve.
Okay, I think I've seen those.
And from these curves, we derive key values. ED is effective dose, the dose causing a specific effect in a certain percentage. EDU means effective in 50% of the group.
Right.
TD is toxic dose, causing a toxic effect, like TDU, and LD is lethal dose. The most famous is LD, the dose lethal to 50% of the test animals.
LDOs, that term comes up a lot in safety data sheets.
It does, and Table 2.6, the Hodge-Sterner table, even gives a rough scale from practically non-toxic to super toxic based on those LDU values for acute toxicity. It helps classify hazard level quickly.
Okay. The notes also mention something called probit analysis. Sounds a bit technical.
It's a statistical method, yeah. It's basically a way to transform that S-shaped dose-response curve into a straight line, which makes it easier to analyze mathematically.
How does it do that?
It converts the response percentages into probit's probability units and plots those against the log of the dose. Figures 2-9 and 2.10 show this. Table 2-5 even gives probit values for different kinds of harm levels, like from fires or explosions, not just toxins. It allows for more precise estimates of things like LDUS.
Okay, so the studies give us the data, the curves, the LD50s. How does that turn into practical safety advice for, say, a workplace? That's where things like TLVs come in, yes.
Exactly. Threshold limit values, TLVs. These are developed by groups like the ACGIH, the American Conference of Governmental Industrial Hygienists. They represent airborne concentrations of substances that, based on current knowledge, most workers can be exposed to day after day for a working lifetime without adverse effects.
They're like workplace speed limits for chemicals.
Kind of, yeah. A guideline for safe levels. And there are different types, as Table 2.7 shows.
Right, not just one number.
No. The most common is the TLV-TWA, time-weighted average. That's the average exposure allowed over a standard 8-hour workday, 40-hour week.
Okay, the standard shift.
Then there's the TLV-STEL, short-term exposure limit. That's a higher concentration you can be exposed to for a short period, usually 15 minutes, maybe up to 4 times a day with breaks, as long as you don't exceed the daily TWA. It protects against acute effects like irritation or impairment.
Gotcha. And the last one.
The TLVC ceiling limit. That's a concentration that should never be exceeded, not even for an instant.
And places like OSHA have their own limits to PALs.
Yes, OSHA sets permissible exposure limits, or PLs, which are legally enforceable standards in the U.S. Table 2.8 lists TLV, TWAs, and PLs for many common substances. They're often similar, but not always identical.
And it's important to remember these TLVs are guidelines for most workers, right? Not a guarantee for everyone. And they're not for general air pollution.
Absolutely crucial points. They're for occupational settings, typical work patterns. They don't account for highly sensitive individuals, and they're definitely not meant for evaluating community air quality or for, say, 12-hour shifts without adjustment.
And the idea behind them is often this threshold concept.
Yes, the idea that for many substances, there's a dose below which the body's defenses, detoxification, excretion can handle it without detectable harm. Now, biologically, any exposure probably has some effect, but below the threshold, it's considered negligible or non-adverse for most people in that context.
Okay, We've covered a lot, routes in how the body copes, the potential harm, how we measure risk and set limits. But it feels like the actual effect on a specific person depends on, well, a whole lot of things.
You're spot on. It's incredibly complex. We've talked about dose paramount and route of entry, how it gets in dramatically affects blood levels, like in figure 2.1.
Right.
But the chemical and physical properties of the toxicant itself matter hugely. Is it water soluble? Fat soluble? That affects absorption. How big is the molecule? Affects excretion, remember. How easily does it evaporate? All these influence its journey through the body: absorption, distribution, metabolism, excretion, or ADME as it's sometimes called.
And how long you're exposed and how often.
Definitely. A single high-dose acute exposure can cause different problems than long-term, maybe lower-level exposure. Chronic effects might build up over time or only appear years later.
And then there's us. We're all different.
Exactly. Individual factors play a massive role. Age, sex, weight, diet, general health, genetics, all influence susceptibility. Someone with existing kidney problems might handle a nephrotoxicant much worse, for example.
And even our body's attempt to fix the problem, metabolism, can sometimes backfire.
Unfortunately, yes. While the liver usually detoxifies, sometimes the metabolic process can accidentally create a metabolite that's more toxic than the original substance. It's called metabolic activation.
Oh, wow.
And ultimately, it all comes down to the interaction at the target site. How much of the toxicant actually reaches the sensitive organ or tissue, and how sensitive is that tissue? That combination determines the final effect.
It really is this intricate web of interactions. It makes you appreciate how challenging safety management must be.
It is challenging, but understanding these basic principles, the routes, the defenses, the types of harm, the dose response, the factors that equips you, it helps you understand why safety procedures exist.
Right, they're not just random rules.
Not at all. They're based on this science.
Yeah.
And knowing this helps you make better decisions, whether at work or home, about potential risks and how to manage them. It empowers you to be more proactive about your own health and safety.
Yeah, it definitely gives you a new lens to view things through. We really encourage everyone listening to maybe think about this in their own context. You know, what potential exposures are relevant to you? What controls are in place?
And, we've only scratched the surface today. Toxicology is a huge evolving field. There's always more research happening, more details being uncovered about these complex interactions. Hopefully, this has maybe sparked some curiosity to look deeper into areas that matter to you.
So as you go about your week, maybe just give a thought to this invisible world of chemicals and physical agents and the incredible work your body does constantly to protect you. It's quite something. Thanks for exploring all this with us today.